graph theory introduction. So, content of this lecture. So, graph theory is a delightful playground for exploration of proof techniques in discrete mathematics, and its results have applications in many areas of computer science, social and natural sciences. In this lecture, we will discuss the introduction and fundamentals of graph theory and how the graphs can be used to model the real world problems. So, the graph theory is evolved out of a practical problem of a Königsberg bridge problem in 1736. Königsberg is a city on Pregel River in Prussia. The city occupied 2 islands plus areas on both banks. So, the problem was stated as under whether the residents of that particular city, they could leave home, cross every bridge exactly once and return home back. So, in this particular figure can see that x, y, z, w, they are basically the islands, and these islands are connected by the bridges which are marked by the double lines which are shown in red color. Now, this particular problem can easily be analyzed if they can be modeled as a form of a graph. So, that means every region or a island, if we can represent as a vertex, and then if there is a bridge between the 2 regions connection or connectivity, then basically we can place an arc. So, this particular map is basically converted in a form of a graph. So, here you can see in a particular graph. Now, once a problem is converted in a graph form, then this particular problem can be analyzed using the model in a graph theory. So, this is the way the most of the practical problems or the applications, if they converted into a form of a graph, then basically the problem can be analyzed and solved. In this particular lecture, we are going to see how different applications can be modeled in this form of a graph, and that is called a graph model. Once a problem is modeled in a form of a graph, then basically we are going to study in this part of the course the theory that is a graph theory, and which is based on the proofs and various techniques, and the algorithms are based on these particular methods. So, as far as the algorithms are concerned, which are basically covered in this graph theory, is going to exploit the structural property of a graphs and how they are going to be represented in a computer, that we are going to see how the graph can be represented in a computer form in a memory, so that the algorithm can exploit this particular model that is called a graph model. So, let us see in more detail about the graph. So, what is a graph? So, graph is a pair of set of vertices and a set of edges. So, graph G is represented as V comma E, where V is a set of nodes and E is a set of edges. So, set of edges is nothing but the pair of nodes. So, this particular graph will capture the relationship between the vertices, also called as objects, and these arcs represents the relations between the objects. So, different applications will pose these relationships, and we are going to get a graph as a model of different applications. So, this particular graph, once it is defined as V comma E and represented as big G, then this particular graph has different parameters, and we basically call a graph with those parameters. Like the order of a graph G, we can represent as the total number of vertices present in the graph. So, when similarly the size of a graph, which is represented as the number of edges in a graph, is basically the cardinality of the edges, and order of a graph is the cardinality of the vertices. So, they are basically the graph parameters. So, in this particular example of a Königsberg bridge problem, which is converted in a form of a graph, we can see the set of vertices, they are number 4 different vertices. The order of the graph is 4. Similarly, the size of a graph is 7 because there are 7 different connections or 7 different bridges which are connecting those vertices. Like we have seen a Königsberg bridge problem, that particular problem was modeled as a graph. So, graphs we can now see is being modeled for different other applications. So, the applications and how the graphs are being formed, we are going to now discuss briefly all of this. So, as far as if it is a communication network, then the graph which we form out of a communication network, where the nodes represents basically the telephones or basically the other instruments, equipments, and edges are nothing but the cables which connects these particular end equipments. So, that is called basically the communication graph. Similarly, let us say the transportation graph comprises of the nodes. Nodes are nothing but the intersection points of a road or basically the airports, and the edges are nothing but the arcs which connects these intersections or basically different airports connected by the flight. So, this is called basically the transportation network. Whether it is a road transportation network, you can represent as a graph. Similarly, the airline or air connectivity of a particular nation, you can represent also in a form of a graph. Internet also you can represent in a form of a graph, where the node represents the classy network and the edges becomes the arcs or the connections between these classy networks, and this all will evolve into a internet, and that can be analyzed. Similarly, the social network, where the nodes represents the actors or the persons and the arcs represents the friendships or the relationships or acquaintances. So, such networks are basically which are used in a social network, that is called a social graph. Similarly, neural networks also can be basically modeled in a form of a graph, where the nodes are nothing but the neurons and the arcs are synapses. Protein networks also similarly we can be defined. So, you see that there are applications, almost most of the applications, where the problem you can model in a form of a graph and do the analysis and solve the problem. So, once a problem is modeled in a form of a graph, then you can visualize the problem, and applying the theory of a graph theory, which we are going to cover in this part of the course, can be used to analyze the problem and solve problem more accurately. Why? Because lot of theorems and the proofs are available. So, those can be used to solve the problem correctly. Not only that, we can also develop the algorithms. Once the graph is represented in a computer, how it is represented in a computer, that we are going to see. Once the graph is represented in a form of a computer, and the theory, using that particular theory, we can exploit the structural properties of a graph, and we can come out with an algorithm. So, in this part of the course, the algorithms which we are going to discuss will exploit the graph structural properties to solve the problems which are there in the applications. Let us see the example of a social network. So, what is the graph here in the social network? So, the nodes represents the persons or the people, and the edges will represent the link between the people or relations between the people. So, the social network graph will look like as per shown in the figure. It is a big graph which will form or which will keep on evolving, where the nodes will come and new nodes are joining the network. So, social network keeps on growing in this particular manner. Road network, how it can be modeled as a graph, we can see over here, where the nodes are nothing but the intersections and the arcs or the edges are nothing but the road segment which connects these intersections. So, we can form or we can evolve a road network, and this can be modeled as a form of a graph. Ecological food web also you can represent in a form of a graph as a model. So, wherein the node will represent different species, and the arcs and the edges are nothing but the prey to the predator. Now, coming back to our graph, so we can see that if the edges or the arcs which will basically have the same endpoints, or the endpoints are equal in the arc or the edges, then it is called a loop. And if, let us say, the edges or the arcs have the same endpoints, more than one edges having same endpoints, called multiple edges. So, it is shown in this particular figure. You can see here that this particular arc is basically the multiple edges, and if, let us say, the edge is meeting at the same vertex, then it is called a loop. Now, a graph which has no loops and also which has no multiple edges, such graphs are called as simple graphs. Some people call them as a regular graphs also. So, in this example, on the right side, this is the simple graph. Why? Because it does not have any loop, nor it has any multiple edges, hence it is a simple graph example which is shown over here. Now, furthermore, we are going to discuss if the edges are present in the graph, what does it means. So, two vertices, if they are having an edge, then they are adjacent, and also they are called as a neighbors if they have the endpoints connected by an edge. So, here this example A and B, they are called adjacent. So, A and B are adjacent. Why? Because there is edge present over here. Now, A and D, there is no edge, hence they are not adjacent. So, finite graph, a graph whose vertex sets and edge sets are finite. That is what we are going to basically assume in this particular discussions. So, null graph is the graphs whose vertex sets and the edge sets are empty. So, null graphs are a trivial graph. We are not going to cover up those particular null graph as a model in this theory of a graph theory. Furthermore, the set of pairwise adjacent vertices is called a clique. These are some of the terminologies which are going to be widely referred throughout this particular lecture. Now, a set of pairwise non-adjacent vertices is called independent set. So, in this example, we can see that u, x and y, they are set of pairwise adjacent vertices, hence this is a clique. Let us say that these two vertices v and y, they do not have any edge, hence this will form a set of pairwise non-adjacent vertices and is called independent set. Now, you can see in this particular graph, you cannot find a clique which is bigger than this particular size, that is more than the size 3. Similarly, you cannot find an independent set in this particular graph example which is having the size more than this size, that is more than 2. Hence, they are basically the biggest or largest cliques. Similarly, the independent set, it is a largest size independent set. Now, a graph wherein the vertices are partitioned into two disjoint independent sets. Independent sets, I have already given you the example which do not have a mutual edge or they are pairwise non-adjacent vertices. So, that means if the vertex Vg is partitioned as two disjoint independent sets in a particular graph, then that graph is called a bipartite graph. So, partite sets of a graph means the independent sets of a graph. So, if the graph has two partite sets, then the graph is called bipartite graph. Example, we can see here all the boys are represented in a form of a set and all the girls are represented in another partite sets, and the graph which we form is called a bipartite graph. So, this is partite set 1, this is another partite set. Similarly, if you are solving the job assignment problem, that is the placement problem. So, here in this particular applications we have the set of jobs which can be represented as one partite set, and the set of workers which can do a particular job will form another partite set. So, the graph which will form out of their relationships is called basically the bipartite graph. So, bipartite graph is going to be very useful wherever this kind of applications where two different partite sets are there and we require a graph to be analyzed with such a relations, that is called a bipartite graphs. So, this particular example you can see that it is written as a matching problem. That means boys and girls, you want to find out a match. Match means the set of edges which will basically, this edge will include one boy and a particular girl. So, set of such disjoint edges is called basically the matching. So, matching problem is the set of disjoint edges. So, you have to find out the set of disjoint edges so that it will solve some problem in an efficient manner, in optimal manner. Similarly, job assignment problem also is to find out those set of match or edges which will basically assign the workers to the job so that it will give the maximum profit to the company. So, that is a job assignment problem. Similarly, the matching problem is to match the boys and girls to for a particular purpose or for particular applications. Now, with this partite set we have seen the two partite sets is called a bipartite graph. Similarly, if there are more than two partite sets, then we have to define a parameter or that is called the chromatic number. So, chromatic number of a graph G is written by chi of G. So, this is a Latin symbol. So, it is a chi of G is nothing but a chromatic number of a graph is the minimum number of colors needed to label the vertices so that the adjacent vertices should receive different colors. Take this example over here in this particular graph. These two edges which are these two vertices which are basically adjacent. So, they are receiving the different colors. These set of vertices, they do not share an edge. So, they are non-adjacent. So, they receive the same color. So, how many minimum number of colors required to color the graph so that no two adjacent vertices receive the same color is basically you can count 1, 2 and 3. 3 different colors are required. So, the chromatic number of this particular graph is 3. So, you can partition this graph into 3 partite sets. What are these 3 partite sets? So, all the blue colored will form one partite sets 1 and 2, let us say. Then there will be a green is another partite set with only one vertex, let us call it as 3, and then there will be another set partite set, let us call it as a 4. So, it will have the 3 partite sets. So, this particular chromatic number is nothing but it will partition the set of vertices of a graph into 3 partite sets. So, this particular graph you can see is a generalization of a bipartite graph which has only 2 partite sets. Here you have obtained more than 2 partite, that is a 3 partite sets, and that particular value is called the chromatic number of a graph, that is represented by chi of G. Now, the maps and coloring of a map is not a trivial problem, and it is a well studied problem in a graph theory. So, map is a partition of a plane into the connected region. You might have seen the atlas as an example. So, how are you going to color this particular map using at most 4 color is a well studied problem. So, the coloring of a map is nothing but coloring these regions of in this particular map using at most 4 colors, so that no neighboring regions receive the same colors. So, any two neighboring region, they are going to receive a different colors. So, how using 4 colors you can solve this particular map coloring problem. This particular map coloring problem can be represented as a graph coloring problem in the following manner. The regions in a map you can be representing as the vertices of a graph, and the adjacency relation between the regions, if you can represent as an edge of a graph, then this map coloring problem can be represented in a form of a graph, and map coloring you can represent in a form of a graph coloring. That means you can find out the chromatic number of a graph and you can check whether it is at most 4 or not. So, that particular problem you can solve using map coloring problem, can be solved using a graph coloring problem. Now, we are going to see more applications here and how the graph theory as a model of a graph can solve this particular problem efficiently or can analyze the problem to the satisfaction of the solution. For example, let us take the scheduling problem. So, we want to find out how to schedule the meetings of different committees with a minimum number of time slots, and this is called a scheduling problem. So, this particular problem you can model in a form of a graph wherein the committees are represented in a form of a vertex, and if there is a member present between these two committees or a particular member which is common into these two different committees, then you place an edge. So, edge in this particular graph will represent the committees having a common member. So, now here we can see that this particular committee is represented in a form of a vertex. So, different committees are represented in a form of a vertices of a graph, and between committee 1 and committee 2 there is a member present which is common. So, basically they are represented in a form of an edge. So, this having formed a graph out of the entire problem setting, we can find out the chromatic number of that particular graph. Having known the chromatic number of a graph, we can find out the how many minimum number of time slots required to schedule all the meetings, and hence you can solve the problem in this particular way. So, therefore, the scheduling problem basically making it as an equivalent to a graph coloring problem. So, if you know how to solve the graph coloring problem, we can solve the scheduling problem very well. Now, let us quickly take up some of the definitions. Those definitions we are going to quickly see their path, cycle, walk, trails. Path, a sequence of distinct vertices such that two consecutive vertices are adjacent. For example, V1, V2, V3 and V4. There are 4 sequence of vertices. All these vertices are distinct in the sense they are not repeated again, and any of these 2 vertices are adjacent. That means V1 and V2 they are having an edge. Similarly, V2 and V3 is having an edge, V3 and V4 is having an edge. So, this is called a path. Cycle is a closed path. That means after V4 if there is an edge to V1, then it is called a cycle. Walk, a walk is a list of vertices and edges such that for a particular edge EI, it has the endpoints in Vi minus 1 and Vi. So, for example, if this edge is EI, E1, E2, E3 and E4, so you can write down the vertex V1, E1, V2, E2 and so on. So, for a particular edge EI, it has basically So, here we have to write down V0, V1, V2, V3 to have these particular notations V0, V1, V2. So, a particular edge EI has the endpoints as Vi minus 1 and Vi. So, having this kind of list of vertices and edges is called a walk. A trail is a walk with no repeated edges. So, if the edges are distinct in a walk, then it is called a trail. So, in this example, A, D, then C, then B, then E, this is a path. Subgraphs. Subgraph of a graph G is a graph H such that the set of vertices of that subgraph H is a subset of vertices of that particular graph G, and the set of edges of the subset of a subgraph H is a subset of edges of a particular graph G, and the assignments of the endpoints to the edges in H and is the same as in G, then it is called a subgraph of a, then it is called a subgraph of a graph G, and that is represented as an H. So, in this particular example, we can see here that if this is the graph which is given, then H1 is a subgraph of G. So, H1 is the subgraph of G. So, H1 you can see C and D. So, this becomes a subgraph of G. So, all the incident edges to these vertices is basically of a subgraph. H1 is also present in the main graph, hence it satisfies the definition of a subgraph. H2 is also a subgraph of G. So, H2 is a graph and it is also a graph. So, H2 is a subgraph of G. Now, we can see A, B and E, D. So, A, B and E, D. So, the edges which are present, this is not present. So, all the edges which are present in H2 are also present in G, hence this particular, and also the set of vertices which are present in H2 are also basically the subset of the vertices of G, hence H2 is a, hence the graph H2 is a subgraph of G. We can see that AE, this edge is also present, vertices are also present in G. Similarly, B, C, D, this particular component is also present, hence the entire graph, that is the graph H3 having two components is a subgraph of G. So, we have seen the definition of a subgraph and some examples for it. Now, we are going to see the definitions, some more terms and definitions. Here we have seen that the graph H3 has two components, is not a connected graph. So, therefore, we have to see what do you mean by a connected graph. So, a graph is connected if for every pair of vertices there is a path, then that graph is called a connected graph, otherwise it is disconnected. So, the example of H3 is a disconnected graph, and this is a connected graph, and this is a connected graph. So, if it is connected graph between any pair of vertices, there is a path. Similarly, between A and E there is also a path. For example, A is connected to E via D, or A is connected to E via B. So, there is a path between A to E. So, there are more than one paths, but it says that at least one path exists between any pair of vertices. So, that exists, hence H2 is basically a connected graph. So, H1 and H2 they are connected graph, whereas H3 is basically a disconnected. This is very important definition to be noticed. Now, another important concept here is called isomorphism. That means the graphs you can form the way you like to form. Take this example, the graph G. You can represent this particular graph G in another way. So, that means W, X, Y and Z you can represent using an arc like this, and this arc will also go like this, and this is an arc. So, both these graphs are isomorphic in the sense that this particular connection between W and X, either you can represent using a line or you can represent as an arc, the way you like to have. All these connections are preserved in the other graph. So, all the relations and all the vertices are preserved, then it is called isomorphic. So, this called as G is isomorphic to another graph and is represented by this particular notations. So, whenever there is isomorphism between two graphs, that means there exists a bijection function f, which will basically do a mapping from the set of vertices of G to a set of vertices of the another isomorphic graph, that is H, such that any edge which is present in G will implies or by implies that edge in that corresponding mapping to another graph H should also be present as an edge. So, that means all the adjacency relations are preserved by that bijection function. So, if you can come out with a bijection function between two such graphs, then those graphs are isomorphic and they are written in this particular manner. Few more definitions. As I told you that the adjacency relations are preserved by a function in isomorphic graphs or using isomorphism. So, we are going to see adjacency, incidence and degree, these three definitions. Now, the vertices J and K, they are called adjacent if they have an edge which connects both these particular vertices. That edge is said to be incident upon, so this particular vertex and this edge, you can say that this edge is incident on this particular vertex. So, degree means degree of a vertex Vk is the number of edges which are incident upon Vk and is represented by that degree of Vk. So, let us take the degree of Vj is nothing but how many edges which are incident. Here we can see only one edge Ei is incident. So, the degree of Vj becomes 1. So, whenever we are counting the degree, we are basically finding out the incidence, how many edges are incident on that particular vertex, and that becomes a degree of a vertex. I told you that the graph can be represented in a suitable form so that it can be stored in a computer memory. So, we are going to see what are those suitable forms. One way you can represent a graph, that is called adjacency matrix. So, given a graph GVE having an n vertices and m edges, we can form an n by m matrix, and that matrix is called adjacency matrix, wherein each element Ai is the number of edges in G with the endpoints between Vi and Vj. For example, y and x. So, y and x, if you take this particular example, x and y. So, between y to x there are two different edges which are basically having the connectivity. So, Aij entry will be 2. Similarly, x to y is also 2y, because from x you are having two different edges between these endpoints vi and uj. So, on the row the set of vertices, similarly on the row also set of vertices, these vertices how many edges basically are connecting them, how these edges are, how these vertices are connected, and this particular connectivity of this representation of a graph is called adjacency matrix. So, this is the adjacency matrix representation of this particular graph G. Now, another way we can represent and store the graph in a computer form or in a memory, computer memory, is called incidence matrix. Incidence matrix, incidence, I told you that a particular vertex vi, how many edges are incident, that relation is being modeled. So, on one side it will be a set of vertices, on the other side it will be a set of edges. So, for example, x is a vertex. So, you can see that a is incident on edge or a incident on x, so it is 1, then c is incident on x, so it is also 1, and d is also incident on x, so it is 1. So, such a representation is called the incidence matrix of this particular graph G. There is one more way to represent the graph, that is called adjacency list. Adjacency list representation of a graph. For example, this is the graph. So, for every vertex x, y, z, w, you can find out the list of nodes or vertices which are adjacent. For example, x will have its adjacency list as w, then y, then only w and y it is basically adjacent to. Similarly, y is concerned, it is adjacent to w, then x, and then z. Z is adjacent to y and w is adjacent to x and y. So, such representation is called adjacency list representation of a particular graph. Now, you can see the all three representations you can easily express as a data structure in any of the programming language. Matrix you can also express, and adjacency list you can express in the form of a linked list representation, and basically the graph is represented in this way, and thereafter you can apply the graph theoretic algorithms which we are going to discuss in this part of the course. We have seen one graph that is called a bipartite graph. We are going to see another graph which is called a complete graph. So, complete graph is a simple graph whose vertices are pairwise adjacent. So, here in this particular graph having 5 nodes, all these vertices are basically pairwise adjacent. So, pairwise adjacent means this vertex is adjacent to any of these pairs. You see that there is a connection. So, also all the vertices, hence it is called a complete graph. Now, complete bipartite graph, it is also called a Biclique. If it is a bipartite graph and having the adjacency relation to all other vertices. So, for example, this vertex is adjacent to all other vertices on the other partite sets. Similarly, this vertex is having the adjacent to the other partite set. Similarly, this one. Similarly, these vertices are also, hence it is called the complete bipartite set. So, complete bipartite set is a simple bipartite set, simple bipartite graph such that 2 vertices are adjacent if and only if they are in different partite sets. Now, another special graph which we are going to just mention is called a Peterson graph. So, Peterson graph is a simple graph whose vertices are 2 element subsets of 5 element sets and whose edges are the pair of disjoint 2 element subsets. So, this is called a Peterson graph. This is the example of a Peterson graph. So, here this is the diagram of a Peterson graph, and different drawings of a Peterson graph is also given. So, let us conclude this particular discussion. So, in this lecture we have given you a very important notion how a problem, different applications you can model into a form of a graph, that is called a graph model of a application, and you can analyze thereafter. So, here we have introduced the basic concepts and the formal model of that particular graph theory and how the graphs can be used to model various problems. In the field of computer science, it is the graph theory is mainly used to solve problem or to represent the complex scenarios, and most of these scenarios will evolve towards a network, and hence represented in a simple form, that is a graph. You can do the illustration, you can view that, and you can basically do the analysis and solve the problems underlying that applications. So, in the upcoming lectures, we will try to give an insight out on its detailed concepts that will give a good understanding of further details, in the sense having expressed the problem in the form of a graph model and having represented the graph in a form of either the incidence matrix, adjacency matrix, or adjacency list, that is the computer representation. So, now we can exploit the structural properties of a graph to solve various problems using the algorithms and using the theory that we are going to cover up in the further classes. Thank you.